that the magnetizations in that landscape, they're correlated, that's it, right?
Let me elaborate on that a little bit. So what I mean when I say that is let's go to this expression here, right? So we look at delta m of x squared averaged. Let's look at a somewhat more complicated object. Let's look at delta m of x, delta m of y, and average that. Okay. So that's the magnetization fluctuation at some point times the magnetization fluctuation at another point, and that averaged. So that is the correlation function we would call chi of x minus y, because once we average, on average it can depend only on the distance between the two positions. Okay? It can't depend on the positions themselves. Okay. And that thing turns out to fall off exponentially in either the ferromagnetic or the paramagnetic phase. So it will go like e to the minus, it's a bit more complicated, there's a power law prefactor, but the important point for this discussion here, it goes like e to the minus distance x minus y over psi. Okay. So here we see explicitly if the 2 points are less than psi apart, then there's a strong overlap, strong correlation between the two fluctuations. If they are farther apart, then that correlation drops off exponentially. And as we approach the critical point, we have to go out farther and farther in order for the two not to talk to each other anymore. So that's what I meant.
You also said there is a power law that
Yes.
takes over.
That's right. That's right. That power law takes over. Yes, that's right. Yes. Yes.
So you are taking the m to be constant. That means you are taking a homogeneous system.
No, not quite. What we are doing is we are saying let's approximate. Let's do an approximation where we replace the position-dependent fluctuating m by its average, and that average we simply call m. Okay? Or in this language here, where I've taken m apart into its mean and its fluctuation, I assume that I just drop the fluctuations because the average of the fluctuation is by definition 0. Okay? So I'm not saying the system is homogeneous. I'm saying I'm replacing the fluctuating magnetization by its average as an approximation.
So is it the spatial fluctuations or the quantum fluctuations that you are talking about?
Both. Now, at the transition we are discussing so far, which happens at a finite temperature, quantum fluctuations are not important. It's all thermal fluctuations. Okay? But you can play the same game, and we will play the same game tomorrow, for a transition at a very low or even 0 temperature. And there are no thermal fluctuations. It's all quantum fluctuations. You still play the same game. You still say, the first thing I will ever try is I just ignore the fluctuations. Okay, and replace my order parameter by its average. And in this case, what I'm then neglecting is quantum fluctuations.
And the criteria would be similar.
Similar, but different. And we'll get to that. Yes. And the important difference will be that here I can make these arguments without ever having to talk about any dynamics. The dynamics are completely separate. I can say I just wait however long it takes for my system to approach equilibrium, and then I calculate the partition function. In quantum statistical mechanics, we can't do that. We'll see tomorrow and the next day that the dynamics and the statics are intrinsically coupled in quantum statistical mechanics. And we cannot possibly talk about thermodynamics without talking about that dynamical exponent z as well. And that will mess up the Ginzburg criteria. Okay? So this will change, but the basic idea will be the same. Any other questions? Yeah, yes.
I know criteria that can be applied to figure out what a critical dimension is. One is Ginzburg, and the other one would be dimensional analysis.
Yes.
Okay. So can you comment on? I always thought that Ginzburg is a little bit more complicated in practice and even conceptually. So has dimensional analysis taken over, or is Ginzburg still used in the field? Or can you just?
Okay. To my mind, that's more or less a pedagogical issue. So I would say you are absolutely correct in saying that once I've learned enough what underlies the Wilsonian renormalization group, I don't have to go through this. I can just count powers. I can just do dimensional analysis, and I'll get to the same answer. And that's a much faster way to get to the answer, and possibly a cleaner way to get to the answer. But it's also less. But that's a subjective statement. It's also less intuitive, probably, unless one has developed a lot of intuition already. Okay. So what I still like about this is that it's so physically intuitive what we are doing here. But the answer is the same. Okay? Now, once I get to the quantum phase transition, it becomes more involved. And so nobody ever does it. We all count powers.
It's interesting that you say that. I've just been in a talk, and it was pointed out that the first argument in favor of dimensional analysis was made by Lord Rayleigh, I think, in 1904.
Probably in the context of turbulence.
Yeah, wave dynamics and stuff.
Yeah, yeah.
The argument was there's nothing more intuitive than that.
Yeah, that's okay. Yes, I also remember when I first looked at the book by Ma, about Modern Theory of Critical Phenomena, I was completely confused. I had no idea what the guy was doing. I was used to taking a Hamiltonian and starting doing Heisenberg equations of motion and actually doing calculations. And I said, what is this? They're just waving their hands and out comes stuff. Where does this come from? So it's a matter of, I think, how one is trained and what kind of thinking one is used to. Yeah.
Can you just go to the first part of this talk when you were describing that Wing diagram?
Oh yeah, let's look at the Wing diagram again. Here's a nice one.
Okay, so in these rings you are actually assuming there's a phase, and this phase disappears when you introduce disorder.
Okay. Well, let's see. So the phase diagram changes. I mean, the only phases we've got here, the only actual phases we've got are the ferromagnetic phase that exists below the Curie temperature and below the critical pressure in zero field, right? So that phase lives in this plane here. And then we've got the paramagnetic phase here, and then we've got the spin polarized phases. Okay. So I would say what changes as I introduce this order, so that's the actual experimental diagram. Now let's go to the cartoon. So what changes now is the relative size of the various phases and regions in the phase diagram. It's actually not introducing or killing any phases. Okay? It just it moves around the phase transition lines between them. Does that answer the question?
Yes. Okay, so I thought there are two different phases, right?
Which ones?
The phase which are separated by these facts.
Okay, so you're asking is the region in between these wings, okay? Is that a separate phase?
Yeah, compared to the phase of the
No, not really. See, everywhere here it's a paramagnet. Everywhere between the little t plane and the wing, it's a spin polarized paramagnet. As I cross the wing, it's still a spin polarized paramagnet, but a different one, because it has a different value of the magnetization. So in that sense, you could say, well, as I suppress the wings, yes, I'm kind of killing a phase. But then you see, you can actually, it's first order, right? So you can always go from this phase into that phase by going around. So it becomes semantics at some point. There's no symmetry being broken by going from here to there, right? So it's like taking a classical fluid and going from liquid to gas by going around the critical point. Nothing dramatic ever happens on that trip, and the same is true here.
What if these two phases have different symmetries?
Then it's a different phase diagram.
Yes.
Okay, that's not the case here. Yes?
Mathematically, we can see that delta n thing becomes less important near the critical point as compared to n squared.
Sorry, say it again. What becomes less important?
This delta n squared. I mean,
Yeah, the delta m squared, yeah.
but I mean, that is mathematically okay. But what is physically going on? Why the fluctuations are becoming less important as we see in the lecture?
As the spatial dimension increases, what happens is that the phase space available to the fluctuations increases. So you see, what we are calculating here, the crucial quantity, is a wave number, a d-dimensional wave number integral over a susceptibility. Now the susceptibility diverges as 1 over k squared in any dimension. But that 1 over k squared, that large susceptibility, gets spread out over d dimensions in phase space. So it gets kind of diluted in the larger dimensions. And that's why. Okay? That's a general statement. Fluctuations, any given fluctuation is always stronger in a lower dimension than in a higher dimension. And the reason is simply this phase space argument here that's encoded in the integration measure in k-space. Anything else? Okay, then I think I've used my 90 minutes, and actually my slides indicate that this is a good break point. So why don't we break here and then continue tomorrow? Thank you.